All right, then let's think again what we have done in the last class. Okay, we started with this model, and this is how we express a model. Okay? According to the model is what? Always model is data generating process, and I believe that the sigma square is first generated from this inverse gamma distribution, and given sigma square and beta is generated from this normal distribution, and given beta, sigma square, and the exogenous variable x, then y is generated from this normal distribution, right? And then so its mean is x beta and its variance is sigma square, right? And also we learned the difference between hyperparameters and parameters. Hyperparameters are non-random, whereas parameters are random variable, a priori, right? So actually parameters are always random variable, okay, in this Bayesian statistics, okay, right? Whereas the alpha 0, delta 0, beta 0, and b 0 are chosen by yourself. So there is no uncertainty about these parameters. Okay, these parameters are control variables. Okay, so that's why we don't put any conditioning the hyperparameters, right? We don't write this sigma square given alpha 0, delta 0, right? We don't do this, right? Okay, and then to estimate the beta and sigma square, then we learned how to estimate the beta first, given sigma square, given sigma square is known. Okay, so that means there's no conditioning, there's no conditioning sigma square here. So beta is generated from this normal distribution, and y is generated from this normal distribution as well, given beta and x, and then and also we treat x as hyperparameters were just purely exogenous variable, right? So x is not random variable. Okay, so then estimating beta means to derive its posterior distribution, the distribution of beta given y, right? Okay, and then to derive its distribution, we compute its density first, because once we are able to compute its density, and then if the density is sort of the standard, then we can figure out what kind of distribution is, right? So standard means that this is a distribution that can be found in a statistics textbook. Okay, so to figure out its distribution, we compute its posterior density according to this Bayes rule. Okay, and then what we want to know is is Cornell rather than a full functional form of the density function. Okay, so then again the f of y is just constant. Okay, this constant, and then f of y given beta is the likelihood, and pi of beta is the prior, and we know that this likelihood is normal density, and prior is also normal, right? And we know the functional form of the normal and normal density, actually the multivariate normal densities, right? So then we just compute the multiplication of likelihood and prior, right? Prior, and then we just arrange this equation with respect to beta, because this is a function of beta, and then also this is density of beta, right? And finally we have this, right? So then this is Cornell of the density function, and then we found that there is an exponent, and then in this exponent I can see quadratic term and just linear term. Okay, so then this means that this is normal density, actually the multivariate normal density. Okay, so then the following question is, what's the mean and variance of this normal density? Okay, from this equation we can be sure that this beta given y must follow a multivariate normal density. So the question is, what's its mean and variance? And to figure out this, we just try to match the coefficient. Okay, to do this, we first assume that the mean is beta 1, variance is sigma squared times b1. Okay, then this is kernel of the density with mean of beta 1 and variance of sigma squared times b1. So that this should be equal to this, right? By matching the coefficient between these two equations, we can compute beta 1 and b1, right? That's what we did, and it turns out that this is the posterior distribution of beta, and this is done with our estimation. Okay. So from this we have Bayesian estimates, and is uncertainty, right? Okay. So then let's go. Excuse me. Again. So then let's understand let us understand these outcomes. First of all, the expected value of beta, posterior mean or posterior expectation. I would simply say the posterior mean of beta, and this posterior mean of beta is b1 times a. Okay, and then if there is only, just intuitively, if there is only, say, okay, just regard this, just disregard this. Okay, here let's go back to here. Okay, suppose we don't have any prior. Okay, that means our prior is very diffusive. Okay, it means what? You may have your own beta 0, but you have no confidence. That means b0 what? b0 must be very small, or b0 must be very, very large. It should be very large, right? Because you don't have any strong prior. Okay, although you have a specific mean, but this is you're just wild guess. Okay, so there is no confidence. It means b0 is very large, or the b0 goes to infinity. Okay, if b0 goes to infinity, what happens? b0 goes to infinity, then its inverse what? Its inverse will converge to what? 0. So 0 times b0, this term is gone, and this term is gone. What remains? The remaining is what? X prime x inverse times x prime y. What is this? This is what? OLS estimator. Okay. So again, you have a diffusive prior. Okay, diffusive prior. You have, we say, we say, if you have flat prior. Okay, that means you don't have any bias to any specific value of beta. Okay, so all possible outcomes of beta can be realized. Okay, with the same probabilities according to your prior. Okay, so then that means your inference must rely on the data itself and nothing else. So that's why your prior mean is exactly the same as the OLS estimator, because you use the information only in the data, and you don't have any prior information, right? So then its posterior mean should equal to OLS estimator. Okay. And also the again, what about its variance? Sigma square times b1, right? And again, b1 is what? That's x prime x inverse, because b0 inverse is 0, right? So then variance of beta is what? Sigma square times x prime x inverse. And this is what? This is variance of OLS estimator. We have seen this before here, okay? This is variance of OLS estimator. This is sigma square times x prime x inverse, right? So if you don't have any prior information, then its outcome must be equal to OLS estimator. So in this sense, OLS method is sort of the special case of Bayesian estimation. Okay. In contrast, if you don't have any data, okay, suppose you don't have any data, what happens? Here, you don't have data, so then you have no x and y. So then this term is gone. Then b1 must be equal to what? b1 should be equal to what? b0 inverse. So then b1 must be equal to b0. What about a? A is what? A is what? Simply b0 inverse times beta 0, right? And then mean is what? b1 times a. b1 is what? b1 is b0. A is what? A is b0 inverse times beta 0. That means what? This beta 1. This time is beta 1, right? Beta 1 should be equal to what? Beta 0. And b1, of course, b1 equals b0. So then what? This posterior distribution of beta is the same as what? Prior distribution of beta, right? It should be. Why? Because you don't have data, so then you don't have data, so then posterior should be equal to prior, because there is no information to update, right? So then in short, if you have no prior information, then outcome must be equal to just OLS estimator. And if you don't have any information in the data, so then the outcome must be equal to prior. In general, the posterior should be in the middle of prior and posterior, depending on how much information you have in your prior or data. So this is purely relative term, right? And this equation shows that here. This is OLS estimator, and this is prior mean. And you see that posterior mean is what? Posterior mean is the linear combination of OLS estimator and prior mean, right? Okay. Let me explain how to derive this. Okay. Again, so this is prior mean, b1 times a, and if we have only one covariance, if we have only one independent variable, so then x prime y is a scalar, x prime x is also a scalar, 1 by 1, and b0 is also 1 by 1, beta 0 is also 1 by 1. All terms are scalar, 1 by 1, right? So then that's why we can express this way, okay? And then I just the denominator. Let me divide x prime x on both numerator and denominator. Okay, so then this is numerator and denominator. Okay, so x prime x inverse times x prime y, x prime x inverse times b0 inverse beta 0. Then this term should be equal to 1, and x prime x inverse times b0 inverse. Okay, right? So then this term is what? This term is just OLS estimator, and then b0 beta 0 is still here. Okay, beta 0 is still here. Okay, and then you see that this term. Okay, so then this term is okay. So then b0 inverse, you can see this b0, and then b0 could, then this can be expressed as x prime s inverse divided by b0, right? Divided b0, and also you can multiply sigma square on both. Sigma square times x prime s inverse divided by sigma square times b0. It means what? The numerator is variance of beta, variance of OLS estimator, and then numerator must be variance of beta. I mean the prior variance of beta. Same for this term, right? So then you can rewrite this equation as this form. Then finally you see that posterior mean is simply a linear combination or weighted average of OLS estimator and prior mean here. And then let's look at this. If what happens to posterior mean if the variance of beta hat is very small? If this is very close to 0, what does it mean by very small variance of beta hat OLS? What does it mean by very small value of variance of beta hat OLS? If the beta hat OLS, the variance of beta hat OLS is very small, it means what? It means what? The OLS estimates is very precise. In other words, data is very informative, right? Because data has so much information. That's why the uncertainty of the beta hat OLS is very small, and the uncertainty of the beta hat OLS is measured by variance of beta hat OLS. Because beta hat OLS is true value? No, beta hat OLS is not true value. This is just estimate. This is just guess based on the data. However, its uncertainty measured by its variance is very small. Then data has so much information, right? So then suppose this is simply 0. Although it's actually this is very close to 0, just take it as 0. What happens? This term is 0. Then 1 over 1, right? Okay, let me do this. This term is 0. Then this term must be 0. 1 over 1 times beta hat OLS. That's just beta hat OLS, and this term is 0. 1 minus 1. This term is gone, right? So then posterior mean is equal to beta hat OLS. Okay, right? In contrast, if this is very large, right? This term is very large. This term is very large, and whereas this term is very small. This term is very small, and just suppose this is 0. This is 0. Then this term will be what? Infinity. Then 1 over 1 plus infinity. What happens? This term is 0. The weight on beta hat OLS is 0. And this term is 0. So then weight on beta 0 is 1. Right? So it means what? Posterior mean is equal to beta 0. Right? So then what does it mean by very small variance of beta? What does it mean by very small prior variance? Small prior variance means that you have so much prior information based on your intuition, experience, or the data prior to Y, okay, and theory. Okay, you have so much information relative to the information in Y. Okay, relative in Y, right? So then your posterior mean should be very close to prior mean, right? So then your posterior is not much updated by the data. Okay. Okay. So this is how you understand the posterior distribution, and this is just This is sort of the key property of the posterior distribution or Bayesian estimation.